Hello and welcome back to Calculus 2. We have the review for the third exam. Tan, 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 tan. Yes, on chapters 8 and 9, and L'Hopital rule is very important, right? Because we are taking a lot of limits in on this test, and there will be also some integration, obviously, right? So, questions, concerns?
Yeah. So, for this example in particular, it's just a general question. So after you actually create your series within Chapter 9, you're working with a problem, and then you use the ratio. For
interval
test.
of convergence.
Exactly, for the interval of convergence. During what situations do you know that you have to actually test it, whether to include it in the interval of convergence or not? Because I don't recall anything like that. But out of my math lab, like here, for example, they were having us replace this, whatever value. In this case, it was -1/4 is less than
Oh,
x
to see the endpoints.
than 1/4. Yeah, should we always be doing that? Like, no matter the scenario, are there certain times we should do it and certain times we shouldn't?
Well, as a rule of thumb, you can always do it.
Yeah.
That's the part. And usually those are simpler situations because you already have the series, and it's not going to be power series. It's just going to be chapter 8. So it defaults back to chapter 8. By knowing chapter 8 well, you already have a gut feeling whether it's going to converge or diverge.
Yeah.
It does bring an important part because your interval of convergence is either including those endpoints or not, or on one side does, on the other one does not, which means either less than or less than equal to. So those are the parts.
True.
So yeah, test it.
Okay. Thank you very
If it's a geometric series, don't test it because geometric series definitely doesn't include, right? So that's one of the parts. So on the exam, guys, 10 questions. I already said definitions of sequence series. So if I state the definition of the series, you will write the sentence, series is the sum of a sequence, right? That's the definition. Define power series, you will write power series definition, which is summation ck x to the n, or ck x to the k. At least one problem where you are testing the sequence, because sequence can converge or diverge, and it's the limit test. And then you have 10 tests for series, which are on the paper I gave you. And those 10 tests you will recognize. I listed here earlier 5 most common tests that are used. Divergence test. And I already told you that you should always check divergence test first, unless you see immediately that the problem is geometric, which converges if r is between -1 and 1, right? Or a p-series. You know, those are extremely easy tests. But then you might have more complicated situations where, you try divergence tests. So you should be able to knock off at least one problem on the exam using divergence if you just run through the entire thing. You must have alternating problem, and then within alternating, you know that if you are on the convergence branch, you are going to hit the series that you need to convert. Be mindful of situations where you can split the series, right? NGIT is by far the master of having that question on every single exam. Like summation of, 3 to the k minus 4 to the k over 5k. This is actually two series. You have 3 over 5 to the k minus series 4 over 5k, right? You can split this. And both of those converge, and both of them you can find individual sums, right? Now, if this 4 was 8, then the one on the left converges, the one on the right diverges, so together they diverge, right? So be mindful of those situations when you have two series that can be split into two separate series, and then check for convergence of both.
Can you do the square root of that and then base it on
Yes, you can do the root test, but those were geometric in this case, so they were easy. You must have ratio test. No question about it. For integral test, guys, make sure you do the 3 proofs.
Well, that means like I can do like 3 minus 8 divided by 5, which would be -1/5, and that'd be like the -1/5 k, which would be like less than 1, which would be
convergent. Yep. Now power series. I wanted to do one of the problems you asked me earlier with limits, because we didn't talk about that, but we should. So power series, guys, know how to get, let's say, 3 or 4 terms of power series. So you're looking at most up to third derivative. So obtain 3 or 4 terms for the Taylor expansion. If it's around 0, it's Maclaurin, but it's still the same thing. So know how to get power series. Know how to compress into a series. That's important skill for differential equations. So that might show up on the test and the final. You get either a sequence with commas or series with pluses and minuses, and then you compress it together into an equation. So this particular was geometric. Now look at that geometric over there, right? You can put 1 to the end and then 1/2 to the end. You know it converges, right? Can you just do the sum right off the bat for this problem? To know what it converges to? First of all, is this convergent or divergent geometric series? Convergent, okay. So what are we going to have as a sum then? What's A, what's R?
A is going to be 1, and R is going to be 1/2.
Nope.
Exactly, only like 1/2. X gotta be greater than or equal to 1.
The base, it has to start at 0, not at 1.
It has to start at 0. So you have to shift the counter. You have to shift the counter, and then you will get that A is 1/2, R is 1/2, and then you will get the answer.
So for power series or what?
And then power series over here.
Explain a little bit more, go a little bit more farther. I mean, why do we have to convert to 0?
Because the definition for geometric series, it has to start at 0.
Okay.
That one starts at 1 over there. So you have to convert to get the correct A. Limits, derivatives, and integrals.
When it's already expanded, and then
Yep.
you want to compress it again after the expansion to show that.
If it's easy, if it's possible. So there were some questions on my MATLAB homework, which I really liked, to be honest with you, that involved limits. I want to take a look at if I can find anything similar.
Oh, yeah, I got a question about the divergence test. I know you say you should do every single one for the quiz and everything like that, but what happened if you said if they go to divergent and if they diverge, how can we do we have to prove it elsewise?
No, that's it. If the limit is not 0, it diverges by divergence test. You're done.
Yeah, but it won't always be like that, am I right?
No. The vast majority will go to 0, and that test will be useless for most of the problems. So you are technically keeping that for maybe one problem that will work for. Maybe 1, maybe 2, I don't know. But everything else is going to be 0 there, and then some of those are going to converge or diverge by a different test.
Should we always test out if it diverged upon the problem itself?
Yeah, you first test that, and then you look for a different method of what would fit.
And what happens if we find out it converges?
You just write convergent. What do you mean?
No, man, like how can we say that?
Well, you would say which test you used.
Yeah, we can't, it doesn't say this test cannot be used to show convergence.
Exactly. That's why it's called divergence test. So it can only show divergence.
Okay.
It's either divergent or inconclusive. That's how it goes. So there are these really cool questions like limit, x goes to 0. 2 cosine 2x minus 2 plus 4x squared divided by 2x to the fourth. So what's the limit for this? Well, I know, I don't know if you know yet, but I know that the cosine theta is expanded as 1 minus theta squared over 2 plus theta to the 4 over 24 minus theta to the 6 over 720 plus dot 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 forever. That means that if I plug in 2x for each theta, because I have cosine of 2x, not cosine of x, I will get that the cosine of 2x is 1 minus 4x squared over 2 plus 2 to the fourth power is 16 x to the fourth over 24 minus 64 theta x to the 6 over 720 plus dot dot dot. To find this limit as x goes to 0, I multiply each one of these by 2, right? Because that's what the problem has. We have this 2 that multiplies the whole power series, which will just, you know, chip into these denominators. So I have 2 minus 4x squared plus, so this is going to become 12, 16 over 12, x to the 4 minus 64, x 64 over 360, right? Yeah. X to the 6 plus dot 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 forever divided by 2x to the 4. Now I also have minus 2 plus 4x squared. So now we see that positive 2 and negative 2 die. Negative 4x squared, positive 4x squared die. And we have the next line, limit x goes to 0. 16 over 12, that's a 4/3. X to the 4 minus, and now I don't care about the rest actually. You'll see why. Divided by 2x to the 4th. So observe that when you divide this, you get 2/3 minus 128 over 360. I know it can be reduced, but actually let's make 64 over 180. X squared plus dot dot dot. You know that the next one over here will be x to the 4th and then x to the 6th and so on. Each one of them goes to 0 because x goes to 0. So every term where x survives is going to go to 0 to infinity. And the only term that survives here is 2/3, and the limit of the whole thing is 2/3. It's a crazy looking limit, right? Problem. That's the limit. It mixes polynomials with trig, right? Polynomials and transcendental functions are mixed together. Yet we are able to construct the power series by replacing those thetas with 2x. And then we plug that power series here, multiply it by 2, and that happens to cancel these two terms. So that's what happened here. I plugged in the cosine series, and then in the cosine series, multiplied by 2, these second two terms cancel, and then you divide by denominator, and then you realize that every next term goes to 0 because x goes to 0. So power series are extremely cool. we get 2/3 as the answer, and that's it. So this is what we have. You can deal with these kind of things, right? For, again, derivatives and for integration as well. You will replace functions that give you headache with the expanded polynomial, let's say 4 terms, and then you go from there. Now, my suggestion to you would be to memorize those 3 power series that are used most of the time. 3 power series that are used most of the time. And that is e to the x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus, and goes forever like that. So that power series is important and used a lot because e to the x is used a lot. And the other 2 are obviously sine and cosine. So memorizing that sine x expands as x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. If you know some mathematics, right, you would know that sine is odd function. So you should have all odd exponents, x to the 1, x to the 3, right? And you're writing the same denominator factorials, right? Power of 3, 3 factorial, power of 5, 5 factorial. And then cosine x is going to fill in the blanks. 1 minus x squared over 2 factorial plus x cubed over, x to the 4th over 4 factorial. And observe that they alternate signs, right? They have plus, minus, plus, minus. You always start with a plus and then just go minus. These formulas are extremely easy to memorize because these 2 complete each other, right, together. And I'm not sure if you see that when you add these 2, right? Do you see that?
No.
1 plus x squared over 2 plus x cubed, right? So if you have all the plus signs, so the players of all 3 of these series are the same, right? They're just separated. Now, a little bit more advanced over here, but it's actually still easy, is to remember sine hyperbolic x and cosine hyperbolic x, which you are going to run into in differential equations. Guys, these are the same power series except they have only pluses throughout. So hyperbolic, you literally write the sine again and just put plus everywhere. So x plus x cubed over 3 factorial plus x5 over 5 factorial plus x to the 7 over 7 factorial. And cosine does the same thing. Cosine hyperbolic does the same thing. You write the cosine and all pluses. So those formulas are easy to remember. So I'm going to box the other ones up there in red, because if you know these, you are significantly reducing your time to do a problem. Because if the question says integrate, I don't know, sine squared, well, you write first 3 terms and then that does a polynomial and just square those, right? Easier to FOIL polynomials and just integrate that, rather than go with the power reducing formula and all of the other stuff that is out there. Oops, why is this not? Did it disappear or I stopped writing? I will never know. Everyone, you guys will probably watch the stream again, so you'll know. But I will definitely never know.
I'm watching you right here. It definitely disappeared.
Okay.
Yeah. That's
Oh,
wild.
all right. Here we go.
We're going to go frame by frame. Yep.
Great.
What do you want us to know tangent inverse as
Nah, you can derive it. That's, you know. So 1 test for sequence, 10 tests for series, the 3 power series that you should know, 2 power series that are easy to remember if you know the other 2. And
this on the quiz as well as sine 8.
what happened?
So he sine hyperbolic x on the quiz. I are explaining to him.
I can ask you to derive it, but if you need it, you can get it because you know the values. 6.10. So another problem that you guys probably seen in the 6.10. Now this is, for instance, this is a good final exam question, right? Prove sine hyperbolic x plus cosine hyperbolic x is equal to e to the x, right? So you have 2 ways to do this. One way is to go e to the x plus minus e to the minus x over 2 plus e to the x plus e to the minus x over 2. And you see that these guys drop. And you have 2e to the x over 2, and that's e to the x.
You cancel out the 2 now.
But no, the 2 stay, right? 2 of them stay. Each one of these gets its own 2.
How did they get their own 2 and 0? You separate them out, am I right?
Yep. You write 4 fractions, and then 2 out of 4 fractions cancel. So that, or you do power series. Observe that these guys only have pluses, right? When you add them together, 1, x, x squared, x cubed, they're all there. So you can do this now in 2 ways. So you can do that as well. So you have 2 different ways in which you can solve that particular problem. It's really cool. All right, anything else that you might be interested in? You know that alternating series has absolute and conditional convergence, right? You know that integral test has 3 proofs before you can use it. You know that most of the comparison tests are comparing something with a p-series, right? You know that you are to ignore sine and cosine in a problem unless they are alternating. So summation of 3 sine n over n squared converges by comparison right away because you just don't worry about the sine n, because it's bounded by 1. So technically you are looking at the problem 3 over n squared, which converges by p-series. Very good, p-series. But if you have a same problem that says 3 cosine n pi over n squared, then that's equivalent to the series of -1 to the n 3 over n squared, and then it's alternating series. So we said that we are not going to ignore cosine of n pi, and we are not going to ignore sine of n pi over 2. Sine of n pi over 2 gives us alternation, and cosine of n pi also gives us alternation. For 0, cosine of 0 is 1, and then sine of 0 What happened?
If I would want to prove to do limit by limit comparison, would I do sorry, the alternating series? Would I do like bk equals 3 over n squared?
Yeah.
Okay.
So that's the alternating series. Root ratio, be mindful of algebra, right? And try not to use too much, common sense or I think or I have a feeling, because, these things are not intuitive. I know I wrote somewhere, I believe it was in 8.6. Let me just try to find, there it is. This stuff. So 1 over n is a sequence, right? There's no summation in front. So that's 1, comma, 1/2, comma, 1/4, comma, 1/8, right? And that converges. And then if you put summation in front of it, it diverges, because harmonic series by p series, right? P is 1, it diverges. But then if you put the alternating, it conditionally converges. So you see that the same 1 over n with slightly different parameters around it, right? Do completely different things. So intuition, and these kind of things, it's good to have a gut feeling and so on, but it could be wrong. It could be misleading. So learn the sheet, right? Use the force. Learn the sheet and apply that knowledge from the sheet, so you don't get into a situation where you say, oh, sequence converges, therefore series converges. Hell no, because here it is, sequence converges, series diverges, of the same thing. So we can't draw those conclusions. What we draw as a conclusion is that a sequence diverges, that diverges. That's true. It's called divergence test, right? If it's not 0 or if it's infinity. So if the limit is infinity, which means sequence diverged, series definitely diverges. That's part of the divergence test.
Wait, what? If you like go negative, it diverges as well if it goes to like infinity.
Yeah. So if the sequence diverges, series must diverge. But if the sequence converges, series might still diverge. There is the example right there. So when we have a convergent sequence, we know nothing about series. Nothing. If we have divergent sequence, series definitely diverges. So you have to be careful making those kind of conclusions. Do not stray from the rules that we covered, the rules that are on the paper. Bueno? Good. Do you have any other questions for me? Any examples or something that we could possibly do? We gotta kill another 20. Yes. Who's gonna go first?
Number 41.
What is the 41?
It's an equals cotangent inverse of 2 to n power, and n equals 1, 2, and 3.
What do you mean n equals 1, 2, and 3?
That's what it says. Consider the formulas for the following sequence. Using a calculator, make a table at least 10 terms and determine possible value for a limit of the sequence, or...
This makes no sense. How can I convert? Yeah, you just get the 3 terms. How can you get 10 terms if they give you n, 1, 2, 3?
No, I mean, they said graph it onto your calculator.
Okay, now...
Just give you the first 3 terms in which it says ...
Oh, and then dot. What the hell happened? So, well, first of all, they say use the calculator, right?
Yes.
Do we use calculator on the test?
No. Only no graphing calculator.
So?
You're not allowed to use this.
So we don't do this problem, right? A1 is the cotangent inverse of 2. A2 is the cotangent inverse of 4. A3 is the cotangent inverse of 8.
Oh, yeah.
And you can calculate on the calculator what that is, and then you can, you know, place those on a graph. 1, 2.
But may I ask you, on a calculator, I know this sounds very stupid, but with the sine and cosine, how would I split the two then with the calculator? Because I know all our calculators can't do cotangent. It doesn't have like a function like that. So how we like split it in the calculator and all?
They have it in the catalog. You don't have it in the main, but if you push the catalog, at least these, there is a catalog button, I believe, around 0 somewhere. And then if you scroll, you should be able to find inverse cotangent. If not, then you have to do more algebra. But again, we don't worry about this particular problem for the test because you don't have the graphing calculator on the test to graph the sequence.
Yeah, but you know this can be like a problem on the quiz and the exam.
Okay, well, we'll deal. I'll deal with that then later. Anything for the exam? Anything else?
The summation of k over 2k.
This one? All right. From, I guess, 1 to infinity, doesn't matter. So when you have a problem like this, whether it's 0, 1, or whatever there, we have a mixture of two different functions, polynomial on top and exponential on the bottom. We see that the limit of this is 0, so we can't use divergence test, right? So we go with whatever else. Now, mixture of different functions is best dealt with ratio test. So we're going to go with the limit. K goes to infinity. We have k plus 1 to the 5th power over 2 to the k plus 1. Absolute values, don't forget that. Times 2 to the k over k to the 5th. So when you peel off 2 in denominator, that's all you can do. You get 2 to the k, which cancels 2 to the k in the numerator. And that works out to be limit k goes to infinity. You have this absolute value of k plus 1 to the 5th over 2 times k to the 5. And that's 1/2. Because you have k to the 5 in the numerator and k to the 5 in the denominator. They are the same order, same exponent. So
It can be 1/2.
front coefficients are 1/2.
Even though it's going to infinity, it can be like going to 0 most about. Like infinite, it goes like infinity over 0. Don't you have to left half rule?
You can. You can try. You will always get 1/2. Because the top
You need this
highest exponent is what?
the 5th power.
5th power. So you have the highest exponent to the 5th on top, and the highest exponent on the bottom is to the 5th. So if you take derivatives, you will get 5k plus 1 to the 4th, and on the bottom you will have 10k to the 4th. Take another derivative, you get 20k plus 1 to the 3 divided by 40k to the 3. You see that the ratio of 1/2 is always there.
Yeah.
Every single time you do L'Hopital's rule, 1/2 is there. So it's much faster if you just remember that when you have same exponents on top and the bottom, ratio of front coefficients is what it takes. They actually ask you to memorize that in pre-calculus for horizontal asymptotes. You know, the ratio of, well, actually the situation with exponents, and then if they are the same, you look at the ratio of coefficients. But then you learn in Calc 1 using the limits at infinity that they represent horizontal asymptote is the application of it, right? And then you have these calculations like that there. There's another way you can do it. You can expand this to the 5th power and then divide everywhere by k to the 5th. That's another way to do the same thing.
Like you're canceling them out pretty much.
And they will all cancel out except the first terms.
But
You will
like,
stay
people
half.
worry about the other terms about like if you have like k to the 4th, k to the 3rd, k to the squared, and
They are all divided by k to the fifth, right?
Yep.
So they all become 1 over infinity, and they all die. The only one that it's important is the one with the highest exponent.
Okay.
That's the only one that counts. All others die in the cancellation. Yes?
What does it mean if you're given like cosine of 2 pi, pi over 2, and then they ask you the first 5 terms in the Taylor series?
You said cosine of what?
Like pi over 2.
Cosine of pi over 2. Well, the way I calculate this is I know the expansion for cosine of x, and then I replace every x with pi over 2 and I compute. So cosine of x is 1 minus x squared over 2 factorial plus, how many terms they want?
4 non-zero.
4, okay. So this is what we get. And I will put the squiggle equal sign here because I don't go plus infinity, right? So now I will replace every x with pi over 2. So I will get pi over 2 squared over 2 plus pi over 2 to the 4th over 24 minus pi over 2 to the 6 over 720, and then get busy with your calculator.
And what if it wanted you to take the integral over a particular area of integration, or a particular...
Is that related to this question?
No, I'm just saying, out of curiosity,
Okay.
so if it was asking you to take the integral of it.
Okay, so is this cool? Okay. So now the question is, what happens if we need to integrate? Well, first off, we are not integrating this, right? Because that's a number. Cosine of pi over 2 is 0.
Yeah.
So we don't do that. But if we are to integrate something, you will do the same thing of expansion. So how about we find a problem? And that's 9.4. So I did one for... I did a problem for limits earlier. Here is the definite integrals. Here is a problem 38. Guys, this cannot be integrated by hand. Sine x squared dx. Right? It cannot be integrated because actually 0.2. From 0 to 0.2. This cannot be integrated by hand because you need another x in front of the sine so you can use u sub, right? This is not sine squared to do the power reducing.
So you want to use the power series?
Yes. So we use either power series or we cry. That's technically it, right? So now you are going to use power series for this one. Now observe your limits of integration. 0 to 0.2, expansion done at 0. It's good, right? So we are going to expand. Now remember, I'm going to write my expansion sine theta because I need to replace every theta by x squared. So I have x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus dot dot dot. And then I replace every theta with x squared. So sine of x squared will be x squared minus x to the 6 over 3 factorial plus x to the 10 over, maybe I should put these expanded denominators, right? 3 factorial is 6 and so on. And now we plug that into the integral 0 to 0.2, and we have x squared minus x to the 6 over 6 plus x to the 10 over 120 minus dot 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 dx. And now you are integrating a polynomial, which is just +1, and then you will be only plugging 0.2, because all of the other ones will be 0, right? There is no plus c because it's a definite integral. So this is equal to x cubed over 3 minus x to the 7 over 7 times 6 is 42 plus x to 11 over 1, 3, 2, 0 minus dot dot dot, computed 0, 0.2. And now it's time to plug in 0.2 and you will get some number as the answer. I don't care. You get some decimal at the end. Any other questions or concerns for the exam?
8.2, number 21.
What does it say?
Square roots.
So what are we supposed to do? So this is a convergence or divergence limit of sequences.
Number 25. I'm really nervous that we won't go get number 25.
1 plus 1 over 2n raised to the n. All right.
She's on the screen. Yeah, but I'm not the screen.
Yes.
Hello.
So we are supposed to take the limit as n goes to infinity of the square root of 1 plus 1 over 2n to the n. Okay. So this is a little bit tricky, but doable. First of all, observe that the form. What do we know? We know that the limit of 1 plus 1 over n to the n is e. That's what we know. We also know that if there is an exponent, the number here is a instead of 1, there will be exponent there, a. And also, we know if the rules of limits, if there is a here, it will also travel as the exponent out there. So, I'm proposing a little substitution. How about we say that k is equal to 2n? See what happens, right? And also, I know that this square root that we have is the exponent half, which will make this n over 2. So before I do a substitution, let's first do that manipulation. So limit n goes to infinity, and then the square root 1 plus 1 over 2n n over 2, right? Because we are multiplying, right? The exponent of the exponent multiplied together.
So you're trying to define it going to 1 pretty much?
Well, we'll see what it goes to. I don't know what it goes to. So now I'm going to propose that k is equal to 2n. From where n is equal to k over 2, right? So I have limit of k over 2 goes to infinity, 1 plus 1 over k raised to the k over 4. The k over 2 goes to infinity. If you multiply both sides by 2, you get k goes to infinity. Because 2 times infinity is still infinity. And I hope you see that this is the equal to e to the 1/4. Because 1 over 1 plus k to the k is e, and then you have the 1/4 in addition over there. So it's e to the quarter, so it converges, this sequence converges to e to the 1/4, which is the 4th root of, right? You can also write it as a 4th root of e, if it makes you smile.
So that's what I did.
Yeah.
Did 1 plus by 2 n to the 1/2, then multiply it to be 2n and times by 1/2, but then I got e squared upon that.
I don't know where to get the 2n over here from.
Man, like it's to like separate them out, like separate out the 2n and then try to get it to be 1, get it to equal.
But then
e.
this has to be a quarter, not a half.
Okay.
You can do that, sure.
I mean, like that's how Professor Armstrong had taught me, but of course I'm really interested in your way, pretty much.
Either way, doesn't matter, just get the right answer. Okay, what else? Anything else? And the preparation. You have something else?
Yes. If she has anything, do you have anything?
Nope.
Okay, number 25. I was trying to get that one.
Number 25? Where is the number 25?
It's a ln problem. Number.
This one?
Yes.
It's not an LN problem, it's 1 over n or 1 over n. What do you mean LN problem?
This is what I did. I said ln y equals 1 over ln y half.
You can't. That's only if you're integrating. All right. Here's one more problem, and we can try and trick this. So you can use ln, right? But maybe we can trick this using the substitution k equals 1 over n. Why not? Right? So this problem now becomes limit 1 over k goes to infinity of k to the k, and if 1 over k goes to infinity, then k goes to 0. K to the k. Now this is L'Hopital rule, right? 0 to 0 situation, which is what you solve with ln's, but now it's much simpler than dragging fractions. So we start by y equals limit k to the k, k goes to 0, and we ln both sides, and now it's calc 1. ln y is the limit, k goes to 0, k ln k, and so k ln k is 0 times infinity, which means we are going to use, I think my battery is dying in this pen, it's acting up. So ln y is going to be limit k goes to 0, ln k divided by 1 over k. So now it's infinity over infinity. So we can use L'Hopital rule now. ln y, L'Hopital, limit k goes to 0. The derivative of ln k is 1 over k. The derivative downstairs is negative 1 over k squared. So all of this is the limit k goes to 0 of negative k. When you cancel everything, becomes negative k, which is 0. So we got that ln y is 0. We e both sides, and we get that y is equal to e to the 0, which is 1. Now you remember that y was the limit k to the k, which was actually the limit 1 over n to the 1 over n. So we know that the limit 1 over n to the 1 over n as n goes to infinity is actually 1. That's the answer. All you do Wolfram alpha and you get it in 1 split second.
Yeah, you said the graphic calculators on test. They didn't say anything about Wolfram. Right?
That's actually true.
Loophole.
Yeah, there is a loophole there. It says no graphing calculators on the exam. Nothing about no tablets with Wolfram alpha.
this one was really difficult. I think it's more difficult than we did. It's like ln sine of 1 over n.
Where is that problem?
Number 29 in the book.
What section?
Oh, 8.2.
Oh, okay. So it's still 8.2.
Yeah.
Problem number
Number 29.
29. Okay. What does it say?
ln of sine parentheses 1 divided by n plus by ln of n.
This is it.
Yeah, I think it's just a multiplication. Am I right?
Not really sure his mindset's
Wait. I'm not fully.
Good luck. See you tomorrow. Good luck, everybody.
Okay. So for this particular problem, I'm going to use again substitution. K equals 1 over n. So k equals 1 over n. I'm getting limit k goes to 0, same transformation. And then I have ln of sine k plus ln 1 over k.
Okay.
Now, the ln of, so I have ln plus ln is going to be sine k over k when I put them together using the log compression. And I still have limit k goes to infinity. Now, later on in mathematics, you learn that these guys can swap, so limit can go inside ln. So we have ln of the limit of sine k over k as k goes to 0, which is 1.
How can it be 1? How is it equal to 0?
So that limit there is 1.
But how can it be 0 if you do like sine of 0 over 0?
The limit is 1. Do the L'Hopital rule.
Okay.
0 over 0, derivative is cosine over 1. Cosine of 0 is 1. 1 divided by 1 is 1.
Let me ask you, if, for instance, if limit as n goes to infinity, if it's, what happens if it's sine of, and what happens if the limit is was inside the infinity?
Sine of infinity is not defined. Limit does not exist.
Does not exist?
Yeah. Limit does not exist.
Okay. And I have so many other questions still.
Yeah, I'll take a look. Let me see.
It's like number 13 is like the example like I told you with chapter 8.3 was the example for number 13.
Yeah. So that's that problem. You have the question?
No, I was just reading the book.
Okay. See you tomorrow.
And like it feels really weird to answer right.
Now let's take a look at that question as well.
I honestly didn't feel like that should exist.
Where is the question?
Number 13 is this one. It says when I plug into 6, I did this. 1, 2, 3, 4, 5.
Summation pi to the k.
Yes.
Well, that's a geometric series.
Yes, I told you I was having that.
Yeah. So r is equal to pi is bigger than 1 divergent. Done.
So the divergent, but the answer doesn't like show that. It honestly, it shows something different. 8.3 number. This one, see, it's 1 minus pi over 7 and divide by 1 minus pi. It didn't show that.
Where is it? Oh, but that's a finite. It's not the infinity. So this is if it goes from 0 to infinity, it's divergent.
Okay.
But yours was finite,
Yes.
so you only have
But we have ever something like that because.
no. because they're not interesting. Is it 1 or 0 to infinity? To 1 to 6?
Sorry, it's 0 to
6.
6.
Yeah. So what you can do is,
This way it asked on the homework.
yeah, so it's pi plus, my pen is not working anymore, so I guess it's time to end it. Pi to 0 plus pi squared plus pi cubed, right? That's it.
That's what I did, but of course it's the wrong answer. It didn't actually specify it was that. It was 1 minus pi over 7 over pi.
Well, yeah, that's the
That's the
compressed form, but
Yeah.
doesn't matter. This is correct.
Okay. I'm correct. So I have a lot of other examples. Like basically it did I hid in my bedroom last night and did a lot of examples.
No.
And
Is
going
this
well.
it?
What?
So just want to end the stream. That's why.
No, I honestly have some more examples from chapter 8.3. Like this one, number 17.
What does it say?
It says 1/4 plus by 1/12 plus by 1/36 plus by 1/8 plus dot 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 plus by 1 divided by 2,916. Yes.
This is so 4, 12, 36, and then 8.
Yeah, this is what I saw. Honestly, the formula. And I thought about taking some. Then I saw it was going to like.
Are you sure it says over 8 over here?
One oh eight.
108.
Sorry.
Oh, this is the problem that was done on the homework. Let me just know. All right.